Welcome back to the Explainer. Let's jump right in. Today, we're running this like an advanced masterclass. We're going to see exactly how a notoriously difficult abstract algebra problem, Conthe's conjecture, is completely resolved using the heavy machinery of the Adelic Langlands Program. If you've ever wondered how modern mathematics crushes seemingly impossible, infinite algebraic loops, you are absolutely in the right place. Here's the roadmap for our proof today. We'll be hitting the ring theoretic problem, mapping the mathematical anomaly, the epsilon factor explosion, Fourier Mukai destructive interference, the Amitsur Core Regularizer, and we'll wrap it all up with the Adelic reciprocity engine. Let's get to it. All right, part 1, the ring theoretic problem. So Köthe's conjecture asks what is honestly a nightmare of a question. If you've got a non-commutative ring with a left ideal where every element eventually multiplies to 0, is the two-sided ideal generated by it also entirely 0? Standard algebra just hits a wall here. So we've got to route this through spectral projection, J-theory, and Lagos field theory to actually find our answer. Now, look at how we translate that totally unmanageable algebra into strict geometry. We map our nil element, we'll call it xi, to act as a local operator. Check out the matrix right here. Because xi is strictly nil, it generates this perfect upper triangular nilpotent matrix in the Hecke stock. All the action, it's forced strictly above the diagonal, no exceptions. And this diagnostic matrix really lays out the exact stakes of the game. On the left side, a valid nil element lands perfectly on the symmetric global nilpotent cone. But take a look at the right. This is our hypothetical counterexample, the anomaly we'll call zeta. If Köthe's conjecture were somehow false, zeta literally deforms the geometry right off the cone and completely shatters the universal functional equation. It's mathematically catastrophic. Moving on to step 2, mapping the mathematical anomaly. This flowchart right here is our master roadmap for tracking the anomaly. Follow the logic with me. If zeta exists, it forces an automorphic excite pattern. Under J-theory flow, that geometric shift generates a ramification singularity, and that sends the local Swan conductor straight to infinity. Ultimately, this triggers a rigid arithmetic veto, basically a hard no from the universe, forbidding the anomaly from existing. To really grasp the mechanics of these equations, we have to define our staging ground, the Hecke stock. Think of this as the specialized geometric environment that parameterizes vector bundles. The absolute secret weapon here is that all modifications are strictly restricted by a flag structure. And here is exactly where that flag structure pays off in the math. That ideal flag modification forces a continuous downward shift in filtration depth. Just look at the main diagonal of the Hecke matrix. Every single entry is strictly bounded to 0. Literally 0 invariant fixed points. It's structural perfection right in front of us. Which brings us to part 3, the epsilon factor explosion. Take a close look at this equation, because things are about to break down. If zeta is not nilpotent, it creates this infinite-type local branch-cut singularity. You see that local Swan conductor term, SWA? That anomaly drives it straight to infinity. And when you plug infinity into the scaling exponent of the global epsilon factor, well, look at the wave graph. It mathematically self-destructs. The macrostability we need is totally annihilated. As the source material so brilliantly puts it, the universe's underlying arithmetic computer simply cannot process an infinite global error phase shift. Lagos field theory steps in as a rigid analytical veto. The product formula absolutely must hold, which means this level of global mathematical contradiction is strictly forbidden. So, how does the system defend itself? Let's look at section 4, Fourier Mukai destructive interference. First, we've got to establish the baseline geometry. The top equation defines the global nilpotent cone. That's the highly stable core of our moduli space. Right below it is the Nilpotent Cone Intersection Matrix. You can think of this matrix as a rigid algebraic lattice. It pairs up all the irreducible components of that stable core to create a massive anchor. And here is that defense mechanism in full action. We pair our rigid, unpolyedate intersection matrix against these highly oscillating complex phases. If our anomaly tries to sneak in a non-zero eigenvalue, that bold lambda zeta you see, the Fourier-Mukai transform forces the deformation through this matrix. The result? Total destructive interference. It's essentially like noise-canceling headphones, but for mathematics. It traps the anomalous eigenvalue and completely flattens it to 0. Because lambda zeta is forced to be identically 0, the generated ideal has to remain strictly nil. The mathematical machinery has just perfectly, structurally crushed our hypothetical counterexample. Next up, Section 5, the Amitsur Core Regularizer. All right, so we've handled the core ring, but what happens when we introduce polynomial extensions? As you can see in step 2, as the polynomial degree m approaches infinity, the combination of these individually nilpotent coefficients creates massive combinatorial overhead. Left unregulated, this infinite chain of variables is a huge threat. It would totally break our local p-adic bounds. But enter this absolutely beautiful mathematical filter. Look at how the unipotent integration matrix acts almost like a funnel. Because it's structurally unipotent, the cross-diagonal terms in the determinant are completely wiped out. This effortlessly decouples that messy infinite product into highly precise, manageable p-adic factors. It perfectly standardizes those infinite variables. And through Euler-Maclaurin regularization, this standardized product becomes the q-Pochhammer symbol, which is the absolute core of the p-adic quantum dilogarithm. I love this part. It's incredibly elegant. It injects a sequence of phantom zeros at every integer point s. These act like mathematical shock absorbers to completely dampen all that combinatorial noise. Notice this really elegant transition here. Down at the core nil layer, where s equals 1, the regularizer evaluates exactly to the topological component counts of our nilpotent cone. But push that to the infinite degree limit, where s approaches infinity, and the terms converge smoothly to exactly 1. Bam! Absolute mathematical stability is maintained. Finally, Section 6, the Adelic reciprocity engine. Here is the final nail in the coffin, bringing the equations together, the Grothendieck-Lefschetz trace formula. Remember how we established that our local Satake operators were strictly upper triangular? Well, that means all eigenvalues on the main diagonal are identically 0. So tracing their Frobenius action inevitably collapses the sum to 0, plus 0, plus 0. It absolutely vanishes. Zero spectral noise injected into the global system. This synthesis unifies our entire masterclass. The Amitsur Regularizer handles the polynomial noise on the left, the trace formula bounds local spectral excitations on the right, and right at the foundation, the Fourier-Mukai matrix crushes the geometric anomalies. Working together, they form this impenetrable mathematical shield around the universal cosmic partition function. So what does this all mean for us? Köthe's conjecture isn't just verified, it's proven to be an absolute structural requirement for the universe's mathematical stability. Which leaves us with a massive question. If this incredible interlocking machinery can flatten the infinite complexities of Köthe's conjecture, what other impossible algebraic mysteries is the Adelic Langlands pathway about to solve next? Thank you so much for joining this explanator. Keep exploring, and I'll see you next time.